Alrighty, so we're working here section 3.6, probability with multiple events. This is suitable for grade 11 students. We're relying on our prerequisite skills, the theoretical probability knowledge that we've already practiced, and tree diagrams that we have already learned as well. Now, we'll work here with Pearl rolling a die 3 times in a row. Now, we have already dealt with a question like this. We know how to handle something like this. We can build ourselves a tree diagram to work here. So I want you to pause the video here, create your own tree diagram. This is a prerequisite skill, so you should have learned it in a previous video. We're not learning it right here, and come back when you have yours completed. I'm just kidding. Okay. We're working here. Pearl, rolling a die 3 times in a row. What's the probability of rolling a 4 each time? Now, we've already dealt with a question kind of similar. We've already dealt with questions similar to this. We could build ourselves a tree diagram. We could have the numbers 1, 2, 3, 4, 5, 6. And then we could take each of those branches that's our first event. We could take each of those branches and create 6 more. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And oh my goodness, all of a sudden we end up with something that's looking really messy, but it's not even the messiest it would get because we're rolling the die 3 times in a row. We've already rolled the die twice, and we would end up with something absolutely wild here because we would have 6s coming all over the place from all of our work. We don't have the time, we don't have the effort, we don't have the space to do this nice and cleanly. We're going to need ourselves a shortcut. Let's consider, instead of rolling a die where 6 things can happen, let's consider what we've already considered before. Let's say we were flipping a coin where we could get heads or get tails. Okay, so we could get heads or tails. That's rolling once, that's flipping once. Heads, tails, that's flipping twice. Heads, tails, heads, tails, heads, tails, heads, tails. Nice and easy. And we would be working with 8 different pathways. That's because there are 8 different pieces in our third row here. 8 different pathways to go through what we're doing right here. That would be what would happen if we were flipping a coin. Now, if we were flipping a coin, that would tell us that to get to our very first layer, we've only flipped the coin once, and there is a 50-50 chance of landing in either spot. That is a 1 out of 2 theoretical probability of just getting heads or tails. Now, from there, if instead we look at our second row, well, at this point, there are 4 different pathways that could bring us here, right? We could get here from heads then heads, heads then tails, tails then heads, tails then tails. Well, if that's the case, there are 4 different ways of getting here. Each pathway to get here has an equal opportunity. That is 1 out of 4 chance because there are 4 total spots. And lastly, our final row here, our final layer, there are 8 different pathways. Each one has a theoretical probability 1 out of 8 of getting there. Now that's great. Let's take a shortcut from there. Okay, so if there are 8 totals from here, each one is a 1 out of 8. Let's get rid of our entire tree diagram here, and instead of making ourselves a super messy tree diagram when we're working with dice, we're going to use this shortcut right here. When we're working with theoretical probability of multiple events, we can calculate that by taking the theoretical probability of event 1 and multiplying that by the theoretical probability of event 2, multiplying that by the theoretical probability of event 3, and that is going to give us the theoretical probability of event 1, event 2, and event 3 all happening together. That's what we're looking for right here. If we had more events that we were working with, we would multiply those together as well. In this case, we're rolling a die, and we're checking the probability of rolling a 4 every single time. Well, that we know from our previous theoretical probability work that the theoretical probability of rolling a 4 once is 1 out of 6. That means the theoretical probability of rolling it again would also be 1 out of 6, and the third time would be 1 out of 6. We can handle this multiplication. We've been multiplying fractions for a long time. When we multiply fractions, we multiply the numerators all across. 1 times 1 times 1 equals 1. Then we multiply our denominators straight across. 6 times 6 times 6 equals 216, I believe. So we're working right here. That tells us that the theoretical probability of rolling a 4 each time, each individual time is 1 out of 6, but rolling a 4 3 times in a row, we're working with 1 out of 216, which is quite rare, which makes sense. 4 times in a row, we're not expecting that to be likely. So what we're working with here, the lesson is we can multiply the individual probabilities together to find the probability of all of them happening consecutively. So we're looking here, we have a problem with some mistakes. I encourage you, read the problem, pause the video, try and find the mistake yourself. Pippi draws 2 cards from a regular deck. If she doesn't put the first card back before drawing the second card, determine the theoretical probability of drawing 2 diamonds in a row. Well, we know the theoretical probability of drawing 1 diamond is 13 over 52. Because there are 13 diamonds in a deck of cards, there are 52 total cards in the deck. So that looks correct to me. Now, if we follow the same pattern that we learned before, we know, okay, well, the theoretical probability of it happening twice in a row, we just multiply the same number. The thing is here, she does not put the first card back. If she does not put the first card back, there are no longer 13 diamonds in the deck. Now there are only 12. If she does not put the first card back, there are no longer 52 cards in the deck of cards. There are now only 51. So instead, our theoretical probability would be 32 over 52 times 12 over 51. We throw that into our handy-dandy calculator. 13 times 12, we end up with 156. Good, and 52 times 51, we end up here with 2,652. Now this would be a really good case if you're caring about the final answer. 156 over 2,652, not very intuitive in our mind. It's very difficult to picture that. So rather than working with a fraction here, we could reduce this. That sounds like a lot of work. We could throw this right into a percentage. That is 156 divided by 2,652, and multiplying it by 100, we end up here with a percentage 5.88%. That is the theoretical probability of drawing 2 diamonds in a row. I want you to take that logic, I want you to try out part B, try out part C, correct the mistakes that were there, and D as well, and then come back, see how you did. Good, so we're changing our fractions like so. First here, drawing a diamond followed by a heart. Well, if we're following a diamond by a heart, there are still 13 hearts in the deck, so that numerator looks correct to me, but there are 51 total cards in the deck, so we'll have to change that. Drawing 2 black cards in a row. There are now 25 black cards in the deck after drawing the first one. There are now 51 cards in the deck. Drawing 2 face cards in a row. There are now 11 face cards left in the deck after drawing the first one. There are now 51 face cards left in the deck. So you can, as we did up here, you can adjust the total calculations, see what you get. Lastly, we have one more question, one more problem that I want to go through. If there is a 50% chance that Tuesday is a sunny day and also a 30% chance that Tuesday is windy, what is the probability that Tuesday is both sunny and windy? Okay, so we have our 50% and our 30%. We know now that the theoretical probability, or that the probability of 2 events happening comes from the product, comes from multiplying the 2 individual probabilities together. So we could work with percentages here. So we're working right here, the theoretical probability. There are 2 different conditions right here. So this comes from the theoretical probability of condition 1, which is like event 1, multiplied by the theoretical probability of condition 2. If you tried this out, if you called them events, I would accept that. Now, the first probability is 50%. We could change that to a decimal, 0.50. Our second probability is 30%. We could change that to a decimal, 0.30. And if we multiply those together, we end up with something like 0.15. That is a 15% probability of being both sunny and windy. If you prefer to work in fractions, we can do that just quite all right. Instead of working with decimals, then our second line would look like something like 50%, that's 1 over 2. And also a 30%, that is 3 over 10. We would multiply those together. That is 3 over 20. If we change that into a percentage, we're still working with 15%. So I'm hoping at this point you feel a little bit more comfortable. You know how to handle it when we're working with multiple events, the probability. Nice work.